Hello, everyone, and welcome to OST Live, a weekly broadcast on blockchain, branded tokens, and token economies built on OST. Open Simple Token, or OST, is a public blockchain platform that allows businesses to launch their very own branded token. Now, on this episode of OST Live, we have a very special guest. We have OST's co-founder and Chief Blockchain Strategist, Benjamin Bollen. Ben, welcome to OST Live.
Welcome, Jose. Thank you for having me.
So on this episode, we're going to cover quite a bit. It mostly pertains to scaling DApps on Ethereum to thousands of transactions per second, which has been a huge topic on Ethereum, a huge topic in the industry over the past couple of years. But before we get into those technical details a bit later, Ben, why don't you tell us a little bit about yourself, a brief background about you. You've been in the blockchain industry for quite some time now. Walk us through your background and how eventually you got to OST.
So we started a year ago with Jason together, but I started in this rabbit hole of a decentralization adventure officially June 2014. I quit my PhD in theoretical physics because I wanted to see if Bitcoin was making a lot of noise in 2013, or at least then, before, but I picked up on it then. And I really got interested in how can you scale to more computational throughput if you add more nodes. And that's sort of the core question that I tried to work on over the past more than 3 years now. 4 years, wow. And so first took me to Scotland, made safe, to end of 2015, 2016, joined the Ethereum community and built the Ethereum implementation on top of Tendermint for Eris Industries, which was very interesting because we'd have more transaction throughput than on proof of work, but you don't have the security properties that proof of work has. And also you miss the core feature of a blockchain crypto economics, right? So I really wanted to move back to the public space, and with OST, I'm very excited to be working back on public Ethereum.
So my understanding is that you and Jason Goldberg, which is the CEO of OST, met up a couple of years ago, and some brainstorms led to you joining Simple Token. How has your experience been over the past year working at OST?
Yeah, I mean, first of all, it's quite a great coincidence. So we were friends already for 2 years, and then over summer of 2017, I was looking how to connect the technical expertise we built to public Ethereum, and Jason was looking how to tokenize an existing Web2 app on top of public Ethereum. And so we had many discussions over the summer, and that's where sort of OST was born. It then created this quite unique company, I think, in the space where we have expertise both from Web2 scaling and Web3 Ethereum background. And so we started with this one question: how do we enable millions of end users that already use applications? How do we allow them to own their tokens on Ethereum? And so the past year has been a very interesting journey. We always wanted to ship, so we shipped OST Kit Alpha, but now we're working on the release that is fully decentralized with the scaling proposals for DApps on top of Ethereum, which we'll probably dive in more today as well.
So what are some of the bigger picture technical problems that OST is trying to or solving for? Is this sort of what you mentioned of allowing platforms with millions of users to use blockchain technology?
So yeah, I mean, so our argument is that we need to contribute to the technology to get actual users on top of Ethereum, right? Because that will really define it to have value if this technology is usable by people without even realizing that they're using it. The same way that people don't need to know how the internet works. They shouldn't need to know how blockchain works. And that sort of motivates the whole stack that we're building, and it relates to different questions. So as an end user, you want to own the value, or our argument rather is that we want to create and empower users of applications to own the value that they're contributing to the platforms, because that's today not the case. But then you start running into, or then you start identifying the problems that you need to address, right? How do you make it very easy for a user to adopt cryptographic tokens before they understand what they are? So how do you transition them without a threshold, so you don't have a conversion drop-off, to adopt these technologies? And then how do you also make it very easy for developers to modify or implement Ethereum into their existing applications, so that we can grow the scope of developers building on top of Ethereum as well? And all that then accumulates into the foundational problem: how do you make sure that you can actually get to a higher transactions per second finalized number as well on Ethereum?
So this is a big, ambitious goal to achieve. It is
a very broad scope. Yes, it's bigger than I imagined. I mean, it's been harder work than I would have hoped for, but we're trying modestly to make some progress. So, yeah. Sorry.
And I think before you've mentioned, so you compared this right now to the internet, and I see that relationship. And personally, I see this with email. Not a lot of people know how it works in the back end, and it's essentially trying to do the same thing. Sort of moving on to Web 3.0, as I've seen you refer it to in one of your talks before. But let's go ahead and dive into one of your major focuses, which is scalability. There has been a lot of talk around scalability and Ethereum, and a lot of other blockchains as well. So why is there currently an issue with scalability? Why is scalability needed on Ethereum?
I mean, why is because we believe that this should be the backbone of the new internet that we're building, right? A decentralized, not censorship-resistant backbone that gives equal rights and opportunities to participate in this essential fabric for society. And then if you believe that that should be the backbone, then we need more than the current amount of transactions we can process on Ethereum directly. A lot of that has to be is related to how security is derived, right? Security for Ethereum as a blockchain is derived from proof of work, and it's the most secure system that we know of today, but it also implies that it is inefficient and that it's costly to run a lot of computing on Ethereum, for two reasons. First of all, everyone has to replicate all of the computation, and so the amount of bits per second that needs to be processed by everyone is growing, and it makes it harder for anyone new to catch up from Genesis, and where Genesis is sort of the start of the blockchain, and verify all the computations themselves. So that number of bits per second that Ethereum as a backbone processes, we want to keep that limited. We don't want to have that grow exponentially, and that's where the concept of sharding comes in. How do you make sure that you can trust the full history, but not need to recompute all the transactions that have gone before? And we can touch a bit on that later. And then the second problem is that as a blockchain, it's an open system, and it can be an open system because it functions on crypto economics. The core argument, in putting it simple, is that you will trust the system because it's more profitable to be supporting the system than it is to try to disrupt it, right? So the rules are set up so that anyone can join, but you will stand to benefit if you contribute to its success rather than trying to disrupt it. And in that sense, Ethereum, as a proof of work system, it rewards miners for sealing a block with what we call a nonce. We can dive into that a bit better, but people tend to notice. So you mine for a block. It's a very intensive process, but that intensive process and very costly process doesn't reward miners for verifying the actual transactions. And so the what is called the verifier's dilemma then concludes that in order for the security properties to be there, the amount of useful computation that is done on a proof of work blockchain has to be small compared to the amount of work that went into finding the nonce, the mining nonce for the block. So that's a core problem that we want to move past, right? How do we build a secure system, but have it be more efficient in the amount of computation that we do?
So it involves the two things that you mentioned: creating a secure system, which proof of work has created. It is very secure, but it comes with the issue of scalability or efficiency, as another term for it. So with that, there's different solutions for trying to create scalable blockchains, and there's also different solutions for trying to create scalable DApps or decentralized applications on blockchains. So can you walk us through what's the difference between a scalable blockchain and a scalable DApp? And I guess we'll jump into from there the different types of scalability or consensus mechanisms that exist today.
Just to pause, like there's some background music. Do you hear that on the record?
It's very minimal. It's can't really.
I can close the window also if you want. I don't know.
It's good for now. It's pretty minimal.
Give me a heads up if it becomes too long. So yeah, I mean, so there's a ton of amazing work that precedes ours, and we also hope to build on that work with a small contribution, but hopefully one that is deemed valuable on this problem, right? So first of all, the problem of scaling Ethereum itself. So how do you make Ethereum as the backbone itself directly process more transactions per second is one of the hardest problems in the space. There is a lot of great work that goes into that, and specifically Casper is Casper FFG. It's Casper, the friendly finality gadget, is one that is relevant to the work that we are doing, and it tries to build on top of what is called Byzantine fault tolerance consensus rules to move slowly. I mean, move not necessarily slowly, but as fast as we can to move away from proof of work miners on Ethereum. That goes hand in hand with sharding, where you want to build a construction where not everyone needs to compute the same information. You only need to compute what is relevant to you. And so the second part of, or the second volume of people working on is how do you build what is called a layer 2 scaling solution. How do you build algorithms and protocols on top of Ethereum such that as an application, you can perform more transactions per second. You can finalize more transactions per second. And in that's the category where the work of Mosaic also falls into. So we're looking to build a framework for scaling DApps on Ethereum.
Go ahead.
Sorry, but and this is already a bit of a teaser, but leveraging or building upon the work of Casper FFG to propose this layer 2 scaling solution.
So these both Casper and sharding kind of go hand in hand with the layer two solutions. So going back to Casper, is
No.
is Ethereum currently pursuing Casper? Is that what's currently running on Ethereum?
So Casper FFG runs on Ethereum. But there's a lot of work. There's active research going into that today. I do want to point out that Casper plus sharding is for scaling layer one. And you would say, for example, plasma chains or payment channels or state channels or counterfactual instantiation, or as we'll talk about, Mosaic is a layer two scaling. What is special about Mosaic is that there's some similarities as a layer two scaling to Casper FFG and sharding.
So I just want to reiterate a little bit about these types of mechanisms. So Casper, to my understanding, tries to implement proof of stake on Ethereum, and then sharding itself breaks down the miners or the validators into different groups, and each group, each individually tackles a certain problem rather than the entire community trying to tackle one problem. And then we move on to layer two solutions like Plasma or payment channels. Can you discuss a little bit more about Plasma and payment channels? Are these essentially side chains or child chains?
So on the first question, so proof of stake itself isn't what we call a consensus engine. And so maybe to give some form of a definition, a crucial part of a blockchain is you could argue for multiple definitions, but I think this one is a useful one for our purposes here. A blockchain is a consensus protocol. And so a consensus engine or a consensus protocol tries to, across a set of participants, tries to get agreement on a certain variable or state of the system. And so proof of stake is a way to make sure that if there are violations of the consensus rules, people or the participants can be punished because they have put up stake. And so they can be rewarded for positively contributing, but they can be punished or slashed for provable violations of the consensus engines. And so proof of stake is one way of holding people accountable, but it's not defining what the consensus rules are. And so Casper FFG is amazing work in that if you, so we mentioned Tendermint, right? Tendermint is a proof of stake layer one consensus engine with Byzantine fault tolerant consensus rules. And to very briefly go into the details here, maybe if you to reach consensus in a Tendermint consensus engine, you need to collect votes from all the validators in 2 rounds. First, everyone agrees on the proposed block, that they've seen this one and deem it valid. Then when everyone sees those votes, they agree that they are ready to commit and pre-commit to it. Casper then builds further on the idea of a validator set being accountable for pre-commit and commit votes, but in the context of what if this consensus engine runs on a blockchain? And so here the blocks already exist, proof of work already produces the blocks, and Casper FFG builds conditions on which the validators can agree that they consider a specific block to be final. Because remember that right now with proof of work, we consider a block final if it has the most amount of work accumulated. And if we want to move away from proof of work, then we need to change what we consider a finalized block. And so I'll need help remembering your actual questions because I went down a rabbit hole again. But we then, when Mosaic built for a layer 2 scaling solution on those consensus rules to finalize blocks off of Ethereum. And so if we briefly also talk about other layer 2 scaling solutions, then for example, a payment channel is specific to transfers, but both parties, if we keep it simple, would put funds into a channel, and then they can effectively exchange signed receipts and only at certain points settle the balances on chain. But then there occur some problems about the data availability of those receipts and also timing constraints if it becomes a more complicated system of when these when the settlement happens on chain. You need everyone to be online to be able to contest certain proposed settlement results. Plasma is a proposal where you think of how to best. I don't often describe Plasma, so give me a second here. With Plasma, you think of a smart contract representing a blockchain on itself, and a designated party with stake reports back what it sees of a bunch of transactions happening off-chain. And so there's different implementations of Plasma. So it's an overarching term of active research and really good research. But you also run into timing issues when this party would report a false state to Ethereum of what has happened off-chain. Then you need to again contest this and potentially exit that corrupted system. And so why that's relevant for us is that we've tried to work on consensus rules that don't have timing constraints in them, so that you don't run into similar problems, where if the chain is corrupted, you now need to challenge that on Ethereum. Yeah, let me pause there.
So now that we have some background on these scalability solutions and how they work, can you pull up some of the slides that you put together for us to sort of show more about OST's solution, which we'll get into next, which is called Mosaic. So Ben, if you can pull up those slides via screen share, and then just
give me a second.
And then we'll jump into discussing what OpenST is, and then from there we'll go into OpenST Mosaic and a little bit of the technical details from Mosaic, including gateway, and then we'll further go into the benefits of Mosaic versus the other solutions that we just mentioned. Great. So I see you have it pulled up.
All right. There's a lot of things on this slide, but maybe here it's easier. So we discussed that that running applications directly on Ethereum is a hard problem, right? You have to, for each application, solve how are you going to scale. And so for each application, time and again, you have to think what is the minimal amount, and which is good practice. I'm not arguing against that, but you have to be very, very careful with what you can compute on Ethereum mainnet. because of its constraints. But as we discussed, that's also where it derives its security. And so what we are proposing, because we want to build a general infrastructure for many applications to scale, we want to extend that Ethereum interface that people already know, writing Solidity smart contracts. So we want to extend Ethereum and its computing capacities, and we called it Mosaic. Mosaic, the name came from the technical description, where we're composing many meta blockchains on Ethereum. And so if you're producing a lot of blockchains in parallel, then now you get a two-dimensional array of blocks, and they have different coloring. So in my mind, you get a mosaic. That's how it came about. But the important question then is, how do you extend Ethereum as a computing interface, right? How do you extend the EVM? And so a thought exercise that you can make is that if you imagine that Ethereum had absolutely no scaling issues, it would be perfectly super performant, cost no money to run on, then you could implement a blockchain on top of Ethereum and then run your application on this simulated blockchain on top of Ethereum itself. It would be somewhat absurd to do, but you could imagine that works. But having that picture in mind of a blockchain fully defined in a smart contract on Ethereum, and so when I say blockchain, I mean the definition that I referred to earlier, that it has a consensus engine and validators can be held accountable using proof of stake to be slashed if they would violate the rules with which they need to reach consensus about what is true. So that's what we call a meta blockchain. We call it a meta blockchain because it's a blockchain on top of a blockchain. And so if you think of it that way, we're just making the problem worse until you realize that you can build the consensus rules in such a way that you can actually do all the hard work of running a blockchain off of Ethereum itself. And that's where the core contribution of Mosaic. We will propose the consensus rules that allow you to define a blockchain on top of Ethereum mainnet, but the very expensive work of finalizing which blocks or which state roots are true, you can actually do on an auxiliary system. And then for that auxiliary system, we use the existing layer 1 implementations of Go Ethereum or Parity or others, don't want to exclude, to extend the same Ethereum interface. And so if you would call this blockchain defined in a smart contract a core, then a core has an open set of staked validators. And their only job is to agree on a state root at the next height in this blockchain. And so what we are then missing is a message passing system between this auxiliary system and this core meta blockchain on top of Ethereum.
Do you think you can make this full screen to view a bit more clearly?
Make it full screen?
Yeah.
Sorry, I was in full screen mode, but I shared the window. So let me reshare just the screen, and then I think that will work. Apologies for that. So much for preparation.
Great.
So I'll put my entire screen, and then I'll go back to. Is this better?
Yeah. Thank you.
All right. Sorry for that. So we have two building blocks that we are introducing within Mosaic. And so Mosaic is a set of blockchains running on top of Ethereum, called them meta blockchains or cores. They have a consensus engine inside the smart contract. With Byzantine fault-tolerant consensus rules, what that means is that if you assume that 2/3 majority is honest, then up to 1/3 of the voting power of these validators can try to deceive you or try to corrupt the system, but they will be punishable if they do so. And so you, as an individual, as a single node or an individual, you have the information to assert which blocks and which part of the history is finalized. But as I sort of alluded, that's too expensive to run on Ethereum. It would be absurd to do this because we're trying to solve for scalability. But by making a few observations, you can prove that you can construct consensus rules that allow you to do this intensive process off of Ethereum. And so now, if you move that process off of Ethereum onto an auxiliary system, you need a way to communicate with that auxiliary system. And so that's what we call a gateway, and we've implemented this right now for ERC20 tokens. Give me a second. Should have done this before. And we will implement this for non-fungible tokens later as well, so that you can also move them from Ethereum to the auxiliary system, and from the auxiliary system back to Ethereum. But this gateway protocol itself consumes the committed state root of the blockchain. And so if you look at this diagram, if you'd want to pass ERC20 tokens from Ethereum to the auxiliary system, then you'd have to move them into the gateway, and the counterpart of the gateway on the auxiliary system will only allow you to extract the tokens as utility tokens. So it's a new representation of the same token at equivalent value. If what is seen about Ethereum is finalized on the auxiliary system, and similarly, you will be able to only move your tokens from the auxiliary system back to Ethereum proof of work if the auxiliary system is finalized and committed onto Ethereum. So if we dive into that a little bit, then the way to make sure that you could recover from this process always is at the first layer you'd have to sorry, first layer is a bit ambiguous because it's the foundational logic is that you would work in two phases. First, you declare a message, which would be, I want to move my tokens to this auxiliary system on Ethereum, giving up ownership of the tokens. And then you confirm that on the auxiliary system. But in order to confirm this, you have to prove it not with a specific signature, but with a Merkle proof. So it's a cryptographic tool that different from signing a message with a private key. It proves that something was part of the state, or it was true on a blockchain. And so by moving the tokens into the gateway will, as a contract, store your message, and then you can actually prove on the auxiliary system, given the state root of Ethereum, that message is stored on Ethereum. And so my message here is I want to move my tokens into Ethereum. When you confirm that with the Merkle proof, you on the auxiliary system, now the co-gateway contract will register this for you and leave the message that you have confirmed it, which allows you to prove that on the origin system, what we call here the progressed state, which would permanently lock your tokens into the gateway contract, at least for you, and then you can prove that you've relinquished full access to the tokens on Ethereum and get access to the newly minted tokens on the auxiliary system. This is a very, very expensive and also slow process, and expensive relatively to just a transaction, because those are reasonably heavy transactions to execute. But then you realize that you can optimize this process in two ways. First of all, as a user, you don't want to be online, so you'd actually want to give this process to a machine, whether that's your own machine or an open set of machines on a network where anyone can pick it up. And we call this type of work done by a facilitator. So we're facilitating this process, but in order for a facilitator to pick up this message that we want to carry to the other side, he needs to put up a bounty. So he needs to give up for this process, a stake, you could call it, but and then he needs to do the proper confirmation of the message on the auxiliary system, which is the confirmation step here. But we can shortcut this logic, because in most cases this will run successfully. And so we can use a hash lock to, with the same secret that the facilitator keeps secret until he has confirmed on the auxiliary system the message. It allows him then to progress the message to the completed state much cheaper, much faster, by just revealing this secret that solves the hash lock. And the reason that the facilitator would do this is that whomever is passing the message, once you pass the message, also rewards the facilitator with a fee. And so the facilitator obviously wants to get that fee, so he will do the confirmation and reveal his secret to progress and get this fee for delivering the message. But now he has also revealed the secret, so if he doesn't go and progress the declaration of the message, effectively permanently locking up the tokens into the gateway, then whomever can come and recover the bounty that he put up to start this process. So he has an incentive to complete both. And similarly, if he wouldn't progress on the auxiliary system, someone else can collect the fee once the secret is known. There's an edge case still where the facilitator would initiate the message transfer but not reveal the secret ever on either side. And to recover for that, the original sender can also declare a revocation message. Sorry, a revocation message. It's not on the slides here. It just gets a bit complicated. But we can also recover if this if this shortcut, if this optimization falls, then you can recover either successfully complete or revert either way the message sending. So that's sort of the important part of a gateway. We need to be able to communicate between these two systems. It's sort of like inventing a teleportation machine because you want to move these tokens from one system to the other, but they can only exist in one place at the same time. But then, and we can go into this on another talk. Once we've now built this new protocol for a gateway, you can then use atomic swaps between the two systems far more cheaply to pass tokens back and forth because they're fungible, right? So it doesn't matter which ones you have, just the amount, which is far faster and cheaper, but it only works because you first constructed a gateway that defines the utility tokens on the auxiliary system, right? So with that, we have the first building block for scaling Ethereum. Or sorry, I said that entirely wrong. Scaling DApps on Ethereum, because now you can move your ERC20 token from Ethereum onto an auxiliary system and back, given that you have knowledge about the finalized state root of the alternate system. And so that's then where the validators play an important role, because disconnected from the message passing, they don't need to know about the message passing. The message passing is purely done on Merkle proof, so it doesn't matter who does it. It's not any trusted signature, so it's not any bridge in a traditional sense or some oracle in the middle. It just consumes finalized state roots. And so the important part then is to build out a validator pool to observe, because we can't finalize Ethereum on the auxiliary system, to observe the auxiliaries from the auxiliary system Ethereum's state root, and then to commit back the finalized state of the auxiliary system onto Ethereum. But it's a lot of architecture. The end result is that on the auxiliary system, millions or billions of transactions can be processed, and it just takes a single commit to finalize them back onto the core contract on Ethereum. And very importantly, as I sort of alluded to, the consensus rules are asynchronous, meaning that there's no time constraints on when finalization information is carried back to Ethereum. And so the very important conclusion from that is that when a transaction is finalized on the auxiliary system, you can consider it committed on Ethereum, even before it has been committed onto Ethereum. And so that allows us to finalize transactions at a very high rate on Ethereum, because we were not introducing, from the asynchronicity of the consensus rules, we're making it possible to add many auxiliary systems onto Ethereum without endangering the security properties, right? Because there is no bottleneck that Ethereum needs to keep up with in order to provide the security for the auxiliary system. And so if we have an auxiliary chain that runs at 400 or 500 transactions per second, and we have 20 of them, then we have effectively finalized 10,000 transactions per second on Ethereum.
So before diving into the benefits of Mosaic, I just kind of want to summarize what we covered here. So essentially, one of the key contributions that Mosaic proposes to the Ethereum community is that it allows for one to move all of the heavy work of running and finalizing transactions off of Ethereum. And so that allows Ethereum to process transactions as usual. So if there was millions of thousands of if there was thousands of transactions, then it would not slow down Ethereum because it's on the work is done off of Ethereum.
Yeah, so one way to summarize it is that tying it back to this original question of the verifiers dilemma, right? If it's very expensive to run computations on Ethereum because they need to be inefficient for the security, then let's make Ethereum the high court, the Supreme Court of what is truth on this infrastructure. But then we leverage the fact that a proof of stake system will, for billions and billions of transactions, not corrupt. So that when it does, we have to revert back to Ethereum, and we can successfully revert back to Ethereum. And the High Court can rule at that spot, or 1 year later, or 10 years later. So there's no timing constraint on it ruling. So if I know that my transaction was finalized, then I know that I can finalize it and commit it onto Ethereum. But we're using as minimal amount of bits, as minimal amount of computation on Ethereum as possible, as needed to finalize the maximum amount of transactions per second that are leveraged on these auxiliary systems. Right? And so, yeah, that was probably not very clear, but it is a very important point, and so that we can fall back onto Ethereum if the system if the auxiliary system fails to reach consensus. And that's an important feature, I think, that sets it apart from other layer 2 scaling solutions, because if an error occurs, you want to be able to recover from it without any timing constraints. It's similar to sort of, we don't run into a blue screen anymore. Like, people who are old enough, younger people than me won't remember this, but back in the day, you would have a fatal error and your Windows operating system would show you a blue screen. We don't have that anymore because we can recover from errors that happen. Obviously, hopefully, we also write better code, but we can recover from errors. And so a lot of this, and similarly also, our chips haven't become that much faster over the past 10 years in just raw number of transaction flops, I guess they can do. Rather, we've innovated on multi-processing, right? We've kept up with Moore's law, in large part because of the engineering work that has gone into smart ways of preemptively computing, evaluating multiple branches, and running processes in parallel. And so the philosophy that we hold here as well with Mosaic is that let's use Ethereum as a very secure message bus and do the majority of the computation on auxiliary systems. But if an error occurs, then we have Ethereum as a strong and alive system to fall back onto and restart and continue without any loss on a new auxiliary system, punishing obviously the validators that failed to keep that system going. And then as a very important note, we do want to move with Ethereum away from proof of work. And as a layer 2 scaling solution, you amplify, you multiply the ability of Ethereum to process transactions. And so as Ethereum moves to would say, correct by construction Casper, then or proof of stake, maybe more colloquially. Then that further amplifies our ability to process more transactions as a layer 2 solution. And additionally, I would hope that also maybe some learnings that this layer 2 scaling solutions can be very fruitful grounds for better understanding the problems that we have to solve for scaling layer 1 solutions as well. Sorry, I'll give it back to you.
So I think you covered some of Mosaic's benefits, which we went over verifier's dilemma. But one thing that we haven't covered yet is that this results in a lower gas price on an auxiliary chain. So everybody knows that Ethereum has gas price to send transactions. So how does Mosaic achieve this low gas price on the auxiliary chains?
So, I mean, I'll preempt this that this is a hypothesis that will have to be borne out by real world observations, right? It's a dynamical system. It's we will know when we run it. But the important point that underlies this argument is that the same verifier's dilemma again concludes that that you need to be inefficient, right? And what that inefficient what that means is you need to pay a lot for the actual computation that that's happening, and that stems from this reward structure that proof of work has, namely that only the miner gets reward for finding the block nonce, and no one is getting the reward for verifying the transactions. And so with Mosaic, we deliberately, I think I actually have a bit of a slide on this here. We deliberately reward the Mosaic validators collectively or collaboratively for verifying the transactions only. So there's not a reward or not for new blocks produced. There's only a gas market for the amount for the gas consumed by transactions on the auxiliary system that is first paid by end users on the system to the layer 1 validators of the auxiliary system. But if they want to have their blocks of the auxiliary system finalized onto and committed onto Ethereum, they have to pay a gas price to the Mosaic validators for the amount of gas consumed. And so you build, you repeat the same model of the Ethereum gas price market, but you change the reward structure for how the validators are rewarded. And so now they are collectively rewarded and to some extent collectively punished for failing to keep the system alive for the amount of gas consumed. And that gas is paid in OST. So OST on Ethereum is an ERC20 token. If you move it into the auxiliary system, it becomes the base token to pay for gas. The important reason for that is that we deliberately didn't want to have a block reward and mint new OST for each block produced. And so we didn't want to couple that to, or it couldn't be coupled rather to Ethereum where new ETH is mined for every new block. And so to escape that, the fee paid on the auxiliary system or the reward for the validators is purely for the amount of gas that is consumed by transactions that actually occurred on the auxiliary system. And so they're collectively rewarded for verifying the transactions, but they also don't have to put all that effort anymore into finding block nonces. So that very expensive hashing and mining effort, they don't have to exert. They just need to verify transactions and cast signed votes on the auxiliary system. And so that drastically reduces their cost. And I'm repeating myself, and rewards them for just the task of verifying transactions. And so the argument then is that you're not in the you're not falling prone to the verifier's dilemma because they're being rewarded for verifying, right? Which would put their cost structure much closer to the actual cost structure of running a node, which is a couple of hundreds of dollars per month, but not millions as it costs for running a proof of work mining farm. So that would be the argument why we expect this gas price market to adjust to far more real in the sense of the actual costs for running a node without mining to execute these transactions. Because again, we're leveraging bytes on proof of work Ethereum.
Great.
Sorry.
And I think this was a good dive into learning a bit about what is out there in terms of scalability, what problems OST hopes to solve, and then diving deep into Mosaic and how it works. Later today, we're going to publish a Medium post, and it will include a summary of what we covered today. And for those of you that are listening to this on a podcast or audio version of this show, you can go ahead and go to the description down below and click on the YouTube link to watch the video version. Ben, I think we covered most of the benefits of Mosaic. I want to go into the live chat now. A couple of you in the live chat have asked a couple of questions. Ben, would you like to answer a couple of the questions that
Of course, yeah, absolutely. I think I somehow got logged out randomly at the end of this, or something wrong. But I'm back, so I don't have the chat history anymore. But if you can,
I'll yeah, definitely. Yeah. So earlier in the chat, and I think you just covered. Well, you did just cover this. So Darren Smith asked, how does OST's scaling solution help address processing resource usage?
So which resource uses?
So Darren is referring to earlier we discussed proof of work and how it requires a lot of energy to be mining those blocks and process proof of work. So I believe Darren's question is towards does Mosaic help address the
Yeah. So I mean, my previous work on Tendermint, like, as a testament for we need to move away from proof of work. Absolutely, but as we today have proof of work, let's try to use the energy that we are expending to finalize billions of transactions rather than doing every transaction directly onto Ethereum. And that's really where the Mosaic consensus rules come in, is that that we allow validators that ability to, with very few transactions on Ethereum, state their agreement that they've agreed on billions of transactions they've verified and be rewarded on Ethereum for the work they've done to verify those transactions. And so that way, at least the amount of effort or energy that we're expending with Ethereum's proof of work, we're using it for vastly more effective computation.
Great. And then one more question, and this one comes from Always, and he asked, is Mosaic a hard fork of Ethereum or an upgrade?
So it is a layer 2 protocol. It's opt-in, so we will deploy it. Anyone can deploy it for themselves, but it's as a DApp, you can opt in to move your logic onto Mosaic, and we will be using it for our own DApp, OpenST.js, where we have a framework for tokenizing applications. We will be using Mosaic just to make sure that we can actually run it, right? So we, as I sort of said at the beginning, we worked our way back from the top. We asked the questions: how do you get a novice user onto Ethereum? And we formulated the framework that we need as a DApp, and then a scaling solution for dApps on Ethereum, so that we can connect this novice user all the way back to Ethereum. And so any DApp, any ERC20 can start looking into this quite soon.
Great. And then this is not a community question, but when do you hope to release the draft paper about Mosaic?
Yeah, so we've been wanting to be very careful about the claims we make, and so we're building the implementation. We internally made the proofs. We're reviewing them in closed circle, but then by the 30th of September, end of September, we are committed to releasing the draft paper to the public.
Great, and I just want to thank you all for listening and tuning in. Just giving out a shout out to those of you in the chat. I see Kid Token, Tyler, Tony, and many of you that are joining us for the second time on OST Live. Thank you for joining the chat. And Ben will be speaking at various events in September, including Berlin Blockchain Week, which is on September 6th. ETH Berlin, he will be presenting Mosaic on September 7th. He will be speaking at Hashed Lounge on Origin Protocol and OST Symbol Token on September 14th in Seoul, South Korea. And then Ben will also be at the Upbit Developer Conference that is in South Korea on September 13th. And thank you all for listening to this episode of OST Live.
Can I make some advertisements here?
Yeah, definitely.
So on the 6th is we're hosting together with Ocean Protocol a token engineering workshop. It's going to be super interesting. So if you're around, please subscribe or try to join. I think we're fully booked, so actually this is a bad advertisement. But we'll see if we can get a bigger venue. But then the biggest advertisement is for ETH Berlin. It's also fully booked, so again, bad idea. But the advertisement I wanted to make was we'll go more in depth on next week at ETH Berlin. So small teaser there.
Great. And then for the developers out there, be sure to check out the code that is on our GitHub, or also communicate with us on our Telegram chat. All the links will be down in the description below. Next Wednesday, we will be having a partner interview, same day, same time. So next Wednesday, September 5th, Sean Howell, co-founder of Hornet and CEO of the LGBT Foundation, will be sharing his experience with launching the LGBT token on OST. And so thank you all for tuning in. You can check out all the links in the description below. And be sure to subscribe to our podcast on iTunes, Spotify. If you're on YouTube, be sure to hit that subscribe button. And we'll see you guys next time.
Thank you.